We all know what the solar system looks like. Mercury, Venus, Earth, Mars, then the giant planets stretching outward toward the edge. But there's one direction those familiar pictures almost never show us: above and below. So what happens if we leave that familiar picture behind and travel straight up? Keep going until the planets, their orbits, even the sun itself are far beneath us. Then turn around and go the other way. At first, both directions seem to lead into nothing. They don't. And the farther we go, the stranger the solar system's place in the Milky Way becomes. The first question is the most important one. What is actually protecting the solar system from the galaxy surrounding it? The answer is the heliosphere, an enormous region of space dominated by the sun's solar wind, a continuous stream of charged particles flowing outward in every direction. It surrounds the planets, extends far beyond the outermost orbits, and pushes back against the interstellar medium, pressing in from outside. At roughly 120 astronomical units from the sun, that solar wind finally runs out of pressure. The boundary where it gives way to the interstellar medium is called the heliopause. Inside it, the sun's domain. Outside it, the Milky Way. For this journey, above and below don't mean up and down relative to Earth's sky. They refer to directions relative to the galactic plane, the orientation of the Milky Way's disk itself. The plane of the planet's orbits is tilted relative to the Milky Way's galactic plane, so traveling perpendicular to the galactic disk takes us through a very different structure than traveling toward its mid-plane. The solar system orbits the galactic center roughly 26,000 light-years from it, and as it does, the sun also moves up and down relative to the galactic midplane, oscillating through the disk over tens of millions of years on a cycle that has been running since before the Earth had liquid water on its surface. Go upward, away from the denser layers of the galactic disk, and the halo gradually becomes the dominant environment. Go downward toward the galactic midplane, and the density of stars, gas, and dust increases. Two directions, two completely different answers. Starting above, leave the heliosphere and head upward, away from the galactic disk. The dense band of stars that forms the Milky Way across Earth's night sky begins to thin behind you. The dusty lanes that block whole regions of the galaxy from optical telescopes fall behind. The younger stellar disk falls behind you, and the older stars of the halo become increasingly dominant. These are population 2 stars, some of them 12 to 13 billion years old, formed when the galaxy itself was still assembling. The Sun is 4.6 billion years old and still actively fusing hydrogen. These stars were already ancient before the Sun existed. They don't follow the neat, flat orbits of the younger disk stars. They move on long, tilted trajectories that predate the disk's formation entirely. Scattered among them are globular clusters, dense concentrations of hundreds of thousands of stars, some of them among the oldest surviving stellar systems in the Milky Way. They orbit the galaxy like slow satellites, essentially unchanged for billions of years. So the halo looks ancient, sparse, and relatively quiet. That assumption doesn't survive long. The visible stars and gas in the halo account for only a fraction of its total mass. Most of the halo's mass is thought to be dark matter, invisible to our telescopes and detectable only through its gravitational effects on everything around it. The rotation of the outer Milky Way cannot be explained by the distribution of visible matter alone. Something is holding the outer stars in. That something is the dark matter halo, a structure so large it dwarfs the visible galaxy and so invisible it has never been directly detected as a particle. The halo doesn't look empty because there's nothing there. It looks empty because most of what's there cannot be seen. Above the solar system, ancient stars, invisible mass, and a structure that outweighs everything you can see. Below is a completely different problem. Turn around and head downward, back toward the galactic mid-plane. The Sun sits roughly 50 to 60 light-years above the galactic mid-plane, according to commonly used estimates. That sounds like a safe margin, but the solar system isn't stationary relative to that mid-plane. As it orbits the galactic center, the Sun moves up and down through the disk over tens of millions of years, crossing the mid-plane, continuing beyond it, and returning again. The exact timing of each crossing is model-dependent, and the solar system has therefore crossed the galactic mid-plane many times since it formed. As the solar system moves through different regions of the disk, the environment changes. The midplane is where molecular clouds accumulate, enormous reservoirs of cold gas inside which new stars begin to form. It is where supernova remnants push shock waves through the interstellar medium across hundreds of light-years. And it is where the solar system isn't simply crossing an imaginary line on a galactic map. It is physically moving into regions where the material between the stars becomes dense enough to push against the Sun itself. When that happens, the heliosphere responds to changes in the density and pressure of the interstellar medium surrounding it. The external pressure on the heliopause increases. The boundary compresses inward. And when the boundary compresses, the heliosphere's ability to reduce the flux of some galactic cosmic rays reaching the inner solar system changes with it. A compressed heliosphere can allow a greater fraction of those high-energy particles produced by supernovae and other energetic events elsewhere in the galaxy to penetrate toward the inner planets. Can that actually affect Earth? Some researchers have suggested a possible connection between these galactic plane crossings and disruptions in Earth's geological record, though the evidence remains contested and the causal chain is far from settled. What is established is that the solar system's external environment can change the size and shape of the heliosphere, and those changes reach the boundary protecting the planets every time the solar system moves through a denser region of the galactic disk. So the contrast is now clear. Above, ancient, sparse, dominated by invisible mass. Below, dense, active, and capable of physically compressing the boundary that stands between the inner planets and the rest of the galaxy. But above and below the Milky Way isn't just empty halo and dense gas. The galaxy has actually thrown something into both of those directions, something that was not discovered until 2010, and something that, by any reasonable reading of the Milky Way's current behavior, should not be there at all. Two enormous lobes of high-energy radiation stretch tens of thousands of light-years above and below the center of the Milky Way. Their edges are surprisingly sharp. Their interiors glow in gamma rays. They are filled with high-energy particles moving at near relativistic speeds, and whatever created them happened millions of years ago. Yet the evidence is still radiating outward today. They are called the Fermi bubbles, identified by astronomers using the Fermi Gamma Ray Space Telescope. They weren't part of the picture astronomers had assembled from previous observations. One stretches roughly 25,000 light-years above the galactic plane. The other extends the same distance below it. Together, they span roughly 50,000 light-years from end to end. The leading explanations involve either powerful activity around Sagittarius A star, the supermassive black hole at the heart of the Milky Way, roughly 4 million times the mass of the Sun, or an intense burst of star formation near the galactic center several million years ago. The exact origin remains an open question. What both explanations share is scale. Whatever produced the Fermi bubbles was energetic enough to erupt vertically through the galactic plane and push material outward through the halo across tens of thousands of light years. They are not directly above the solar system. They are centered on the galactic center, thousands of light years away. But from our position inside the Milky Way, they are part of the enormous vertical structure the solar system is continuously moving through. Sagittarius, a star, is quiet now. The Fermi bubbles suggest it wasn't always. The Milky Way doesn't present itself as a recently violent system from the outside. These structures preserve the evidence that the galaxy's interior history was considerably more eventful than its current appearance implies, and that evidence has been sitting there this entire time, waiting for an instrument sensitive enough to detect it. Which raises the final question. These structures already reach tens of thousands of light years into the halo above and below the galactic center. If the galaxy can throw material that far, how much farther does its influence actually extend? And is there a point where it finally stops? But the farther we travel above and below the galactic plane, the more another question becomes unavoidable. If the halo stretches beyond the visible galaxy, where does that structure actually stop? Travel far enough outward, and you expect the Milky Way to eventually disappear. It doesn't. There is no wall, no final star, no point where the galaxy suddenly becomes outside, because a galaxy doesn't have an edge in the way you think it does. The heliosphere has a boundary. The stellar disk has an outer region. But beyond that, the stellar halo fades rather than stops. The dark matter halo is thought to extend far beyond the visible disk, and eventually, the gravitational influence of neighboring galaxies becomes just as important as the Milky Way's own. At that point, inside the Milky Way stops being a useful distinction. What you find instead of an edge are the scars of everything the Milky Way has consumed. Wrapped around the outer galaxy are streams of stars that were once separate dwarf galaxies. The Milky Way's gravity has been pulling them apart over billions of years, stretching their stars into long arcs that trace their original orbits. The most prominent is the Sagittarius stream, the dismembered remnant of the Sagittarius dwarf galaxy, currently being absorbed into the Milky Way, its stars distributed across a loop that spans the entire sky as seen from Earth. This is what a galaxy's outer boundary actually looks like. The slow, continuous absorption of smaller structures into the larger one, playing out across timescales longer than the Sun has existed. The thing we call the Milky Way is not a bounded object sitting in space. It is a gravitational process that has been pulling matter inward, consuming neighbors, and gradually extending its reach for billions of years. The idea that it has a defined edge where it stops and the universe begins was never quite accurate. And that gradual dissolution, the slow, poorly defined fading of everything the Milky Way is, exists in the same direction as directly above and below the solar system. The galaxy, above and below the solar system, has no edge. It just keeps going. Most people picture the solar system as sitting inside the galaxy the way a ship sits in the ocean, surrounded by it but separate from it, moving through it without being changed by it. That picture is wrong. The same sun that rises every morning is carrying Earth through the Milky Way while simultaneously moving above and below the galactic midplane. The heliosphere changes size and shape as the solar wind and the surrounding interstellar medium change. The cosmic ray flux reaching the inner solar system is not constant. It shifts as the solar system moves through different conditions. The solar system is not insulated from its environment. It is part of it. Above, the galactic halo, ancient and sparse, dominated by a dark matter structure that outweighs everything visible and has never been directly detected as a particle. Below, the active galactic midplane, dense and full of molecular clouds, where the heliosphere responds directly to changes in the density and pressure of what surrounds it, and erupting through both directions from the galactic center. Two enormous structures still glowing in gamma rays, preserving the record of events that occurred millions of years ago in a galaxy that currently shows no sign of what it once did. We are not looking out at the Milky Way. We are inside its machinery, moving through it, shaped by it. Above us is not simply empty space. Below us is not simply more sky. Both directions lead into the structure of the galaxy itself.